Well, hello, and welcome to Doc Onco's physics tutorials. Keith Onco here. Today what we're going to be looking at is the magnetic force on a wire due to the fact that there's two current carrying wires in a particular area. And what I mean by that is if I were to draw a current carrying wire over here, and so I have a current carrying wire with current going to the right. We know that we have a magnetic field that surrounds this wire, all right, and it's surrounding it in a three-dimensional fashion, right? And so if I have a second wire then, like this, I'm also going to have a magnetic field around that wire, right? And these two magnetic fields are going to interact. And we know that whenever magnetic fields interact, there can be an attraction or a repulsion. And that's what we're going to look at today. So what we want to do is, I'll just move this down a little bit here. I'm going to redraw my current carrying wires. This I'm going to call wire 1, and I'm going to call this I1, the current that's going through that wire. And I'm going to call this one I2 for the current going through that wire. Now, there's going to be a force on the top wire that's going to be due to the magnetic field of the bottom wire. And so what we need to do is we need to figure out just how that magnetic field from the bottom wire is going to impact the top wire. So we're going to need to use our right-hand rules again to figure out the direction of the magnetic field above wire number 2. We don't care about what's happening below wire number 2, but we want to know what's going on above wire number 2 because that's where wire number 1 is. So if we use our right-hand rule, all right, and the right-hand rule would be the one where we use the thumb, right, that points in the direction of the current, and then our fingers will curl in the direction of the magnetic field, right? So if I were to do that, and I'm going to see if I can do that here, I'm going to hold up my hand and cover my face a little bit, so you'll have to excuse me. My thumb, right, is pointing to the right, and my fingers are curling this way. So if I try to apply that, right, on top of my thumb, my fingers are curling towards me. So if I look at my picture here in the diagram, on top of the wire, the magnetic field is going to be coming out of the page in the entire area above wire number 2. And specifically what we're interested in is the magnetic field right where our wire number 1 is. Okay? So that's what we're mainly interested in. The magnetic field at wire number 1 due to wire number 2. So we know that the force, the magnetic force on wire 1 is due to ILB sine of theta. Well, since the magnetic field is coming out of the page and the current is going to the right, they're at right angles, so theta is going to be 90 degrees, so the force just becomes I times L times B. Well, what is I? Well, I is simply going to be the current of I1, okay, because that's the wire that we're interested in, right? The force, the magnetic force is equal to ILB, I being the current of that wire. What's L going to be? L is simply going to be the length of the wire that's in the magnetic field. Now, we haven't said what that is yet, so we'll say that the length, L, is going to be, well, let's make it easy, we'll make it 0.5 meters. Okay, so 0.5 meters in length. And let's say that, well, we don't know what B is yet. Okay, we have to figure out B. Let's say that the distance R from wire number 2 up to wire number 1, this will be R here, and let's say that R is going to equal, we'll make it 1 centimeter. Okay, so we have, I think, enough information. We don't know what our currents are, so let's make up some values there. Let's make up a current value for I1 of 3 amps and I2 will equal, say, 10 amps. Okay, well, we now know what I1 is. We know what the length of the wire is. We don't know the magnetic field yet, but I think we'll be able to figure that out. Okay, and so we got to ask ourselves then, well, what is the equation for the magnetic field around a current carrying wire? Well, that equation just happens to be B equals mu 0 times I divided by 2 times pi times R. R being the distance from the current carrying wire out to wherever that magnetic field is. Well, in our case, that distance is going to be the value of R here, right? The value of the distance between I2 here up to where I1 is, that's R, and that's going to be 1/2 centimeter. Okay, so we could substitute in, before we do any substitution, B equals mu 0 times I. Which I is it going to be? Well, the magnetic field, right, up at this point right up here is due to I2. So we should add a subscript in down to that equation over there, which is I2. Okay, so let's go over to the left-hand side of the screen here. So the force on wire 1, the magnetic force on wire 1, is going to be I1 times L times B. Well, what is B? Well, B is simply mu 0 times I2 divided by 2 times pi times R. Okay, so now we're at a point where we can simply plug in some numbers. So let's do that. So let's see, what do we have for I1? Well, I1 we've said is 3 amps. Okay, and L is, what did we say L was? It is 1/2 meter. All right, mu 0 is 4 pi times 10 to the minus 7th power. All right, I2 is 10 amps, all divided by 2 times pi times the distance again from wire 1 to wire 2, and that happens to be 1 centimeter, so 0.01 meters. Always remember to convert your centimeters to meters. So now, when we do the calculation, the number that we come up with is 0.0003 newtons, or 3 times 10 to the minus 4th newtons. So a reasonably small force, but these forces need to be taken into consideration, and it's the interaction of these magnetic fields that actually makes some of the most useful things that we have and that we use today useful, right? Electric motors. Electric motors turn because of the magnetic interactions between some permanent magnets in a motor and the magnetic field that surrounds a current carrying wire. So I hope that helps. The force on one wire due to another current carrying wire. See you next time.